Good morning, dear student. In today's lecture, we will discuss our practical course, that is CHI 434, section first, inorganic instrumental analysis. So, in this practical course, the first practical is to determine the magnetic susceptibility of any two sample. So, whatever the sample, uh, that is the material, okay, which having a magnetic character in them, they are analyzed with the help of they can analyze by different methods, and we can determine the magnetic susceptibility of that material. And depending on this magnetic susceptibility, the materials are classified as diamagnetic, paramagnetic, then ferromagnetic materials. So depending on the behavior of this material in magnetic field, they are classified into different types. So in this lecture, we are very much interested in the magnetic susceptibility of material, how this magnetic susceptibility is find out for particular material. So we are very much familiar with this magnetic susceptibility, and you are also uh, very much familiar because in previous semester there is a one course in which this point is there, that is susceptibility. So you already studied the theoretical concept regarding to this magnetic susceptibility or the susceptibility of the material. So in this lecture, we are very much interested in the determination of magnetic susceptibility by different methods. So there are different methods are used to determine the magnetic susceptibility, but in today's lecture we discuss only the Gauss method uh, to determine the magnetic susceptibility of material, because it is very simple method. Before that, if you consider this magnetic susceptibility, what is this magnetic susceptibility? Magnetic susceptibility, it is denoted by symbol chi. So it is like this, it is denoted by symbol chi, and it is defined as, what is this magnetic susceptibility? It is the ratio of magnetization to the applied field strength, that is m by h. So this is your magnetic susceptibility. It is denoted by symbol chi, which is equal to m by h. That is uh, by the application of external magnetic field, how much the material is how much get magnetized, that is it is temporary magnetized or permanently magnetized, how much magnetic lines of force can passes through this material is nothing but your magnetic susceptibility. So by the application of magnetic field, and the material get magnetized, and how much magnetization is occur in that material is nothing but your magnetic susceptibility. So we already discussed the definition in our regular theory course, that is CHI 432, material science, magnetic susceptibility. uh, so what is this magnetic susceptibility? Material magnetic susceptibility tell us, so what this magnetic susceptibility tell us, how susceptible it is to becoming temporary magnetized or permanently magnetized by the application of magnetic field. And it is defined as magnetization produced per unit magnetic field. Magnetization produce magnetization produce per unit of magnetic field, per unit of magnetic field. So what is this magnetic susceptibility? It's nothing but the magnetization produced per unit magnetic field. So magnetization, it is denoted by symbol capital M, and magnetic field strength, it is denoted by symbol capital H. So magnetization produced per unit magnetic field, it is known as magnetic susceptibility. And with the help of this Gauss method, we can easily determine the magnetic susceptibility of the material, because very simple apparatus is used. Okay, so let us discuss about this Gauss method. Gouy or Gauss method. So the pronunciation you should remember. As per our convenient, we consider it as Gauss method. So in this method, if you consider this Gauss method, in this method, uh, inhomogeneous, not homogeneous, inhomogeneous field, inhomogeneous magnetic field in the central region, in the central region between central region between two flat poles of a permanent magnet, permanent magnet or electromagnet, or electromagnet. So inhomogeneous field is applied in this Gauss method. Not homogeneous, not constant magnetic field is applied. That is inhomogeneous means we can increase or decrease. We can increase or decrease the strength of applied magnetic field. That is inhomogeneous field in the central region between two flat poles of permanent magnet or electromagnet. Then the next important point in this Gauss method, that is sample is field. Sample is field. Sample is field in cylindrical tube. Sample is field in cylindrical tube, which is suspended in such a way that, so this cylindrical tube suspended in such a way that, in such a way that one end lie in the center of the field, one end, one end, one end lie in the center of the field, in the center of the field, in the center of the field, and other is effectively outside, and other is effectively outside, other is effectively outside. So uh, other is effectively outside from the magnetic field, from the magnetic field. Other is effectively outside from that of magnetic field. So this is the 2 point in this Gauss method, or we can consider it is the theory of this Gauss method, that is inhomogeneous field in the central region between two flat poles, that is which is act as a magnet. One is north pole and another is south pole. Central region between two flat poles, or two flat poles of a permanent magnet or electromagnet. And second, the sample is filled in the form of cylindrical tube, which is suspended in such a way that, the center of the field, in such a way that one end of this tube is in the center of the field and other is effectively outside from that magnetic field. So there is a no effect on the magnetic field on other end of this tube. So if you consider uh, this diagram, simple diagram is there. That is, this is the case. This is your north pole is there. Then this is your south pole is there. So south pole is there. Okay. Then this is the tube. tube, and the is connected to the tube is connected to the sensitive balance. The balance is very simple, though it is not your the balance which is used in laboratory. It is the balance which is used when we take vegetables. So in Marathi it is called tarazu. So it is very simple. It is just like a tarazu. It is your sensitive balance. One side it is filled with a different material. It is filled with loads, means certain weights we can consider. So one side of the balance it is filled with weights, and other side it is connected to this cylindrical tubes. So what happened, by the application of magnetic field, when if there is a we can say that if the material is diamagnetic material, then there is a no change in weight. That is, there is a no effect of this applied magnetic field on this diamagnetic material, and the balance get shifted towards the weight, or we can say that there is a no change in weight for a diamagnetic material. We can consider the change, because in this case you should first find out the weight of the sample without application of magnetic field. Let us consider it is a W1 gram, and then the material is placed in magnetic field, and after that we can observe what is the change in weight. That is, either the weight is increases or decreases. So if the weight change is positive, means the delta W is positive, it indicates the material is paramagnetic. If delta W is zero, there is no change, then the material is diamagnetic. And if the we can consider delta, that is when delta W is zero, that is the change in weight is zero, then it is non-magnetic material. When delta W is positive, then it is your paramagnetic material. So just we find out the change in weight. That is, we are very much familiar with this concept, that is we generally used in gravimet. And when the W change in weight is negative, then it is a diamagnetic material. The diamagnetic material should be there. So this is the concept. So initially you take the weight in absence of magnetic field, that is your W1 gram, and then by the application of external magnetic field you just find out the W2, and then you have to find out the difference, that is W2 minus W1, that is your delta W. And so with the help of this we can easily determine the material, either it is diamagnetic, paramagnetic, or non-magnetic material. So in this case, and this is north pole, this is south pole, and this cylindrical tube is attached to the your sensitive balance. So in this case, if you consider in absence of field, in absence of magnetic field, the weight of sample is W1 gram. Second, in presence of field, the weight of sample, that is W2 gram. The weight of sample is W2 gram, and change in weight of the sample. The third one is the change in weight of sample. The change in weight of sample, that is W2 minus W1, we get delta W grams, that is change in weight. Okay, so initially you have to take the weight of a sample in absence of magnetic field, it is considered as W1. Then in presence of magnetic field, after application of magnetic field, then W2, and the change in weight, that is W2 minus W1. Then you have to find out delta W gram. So whatever the force acting on the sample by the magnetic field, it is your delta W gram. So whatever the force acting on sample, it is your delta w gram. Let us consider this as equation 1. And force due to the magnetic field, the due to magnetic field force due to magnetic field, it is given as 1 by 2 k1 minus k2 h square into a into mu 0. Let us consider this as equation 2nd. So whatever the force acting on the sample, it is equal to the delta w gram, and the force due to the magnetic field, it is given as 1 by 2 or half k1 by k1 minus k2 h square a mu 0, where k1 is your volume susceptibility of sample, then k2 is your volume susceptibility volume susceptibility of air. H is your magnetic field strength, A is your cross sectional area. So H is your magnetic field strength and A is your cross sectional area. A is your cross sectional area, and mu 0, it is your permeability, and it is equal to 1 for air. Permeability in air is 1. So from this two equation, that is equation 1 and equation 2, we can write that is w gram, delta w gram, which is equal to half k1 minus k2 h square into a, because mu 0 is equal to 1, the permeability in air is equal to 1. So from this equation we can write delta w gram upon 2, which is equal to k1 minus k2 delta w gram upon 2, not upon 2, I will make a mistake here. So in this case, this 2 get multiply, so delta w gram into 2 divided by h square into a, which is equal to k1 minus k2. So we get this k1 minus k2. From this equation, k1 can be written as k1 which is equal to k2 plus twice delta w gram upon h square into a. So we get this equation. So what we get? So let's discuss here. What you get actually after equation 1 and 2, after solving equation 1 and 2. So k1, that is twice delta w upon h square a, which is equal to k1 minus k2, and therefore we get k1 which is equal to k2 plus twice delta w upon h square a. And so this is the equation. And from this equation, the susceptibility gram susceptibility we can easily find out the gram specific susceptibility, uh, that is, which is equal to k1 upon density. So k1 upon density, so we can write this as k1 upon density, which is equal to, we can write this as 1 by density in bracket k2 plus twice delta w h square into a. And similarly, The molar magnetic susceptibility. The molar magnetic susceptibility. Molar magnetic susceptibility, which is equal to, that is it is denoted by symbol chi small m, which is equal to k1 into m upon density. So we can write this as m by density in bracket k2 plus 2 delta w h square into a. So if all these terms are known, then we can easily find out the molar magnetic susceptibility or gram magnetic gram susceptibility, gram specific susceptibility. So this is the Gouy method to determine the magnetic susceptibility of material. So this is very simple method. So with this formula, we can easily find out the gram specific susceptibility and molar magnetic susceptibility. So this is all about this first practical. In the next lecture, we discuss the remaining practicals of our section first. Thank you.